topic for today. And that is AC power or power in AC circuits. Okay, it's a short topic, about 7 or 8 slides. And there are a couple of example problems that we'll do on Wednesday. Okay, so electrical power. Electrical power is transmitted over long distances. You may have seen overhead electrical lines, right? There are some coming over the mountains or going over the mountains. If you go to the parking lot of Sprouts, there is a big tower right in the middle of the parking lot. I didn't realize it until after, like, a few weeks later. I've been parking right next to it. That's when I realized there's an overhead line running right through the. So electrical power is transmitted over long distances. It flows from the utility company to the consumers. Consumers are of two kinds, industrial as well as residential. Most residential consumers do not have to worry about reactive power. And what is reactive power? That is what we will study and look at in this chapter. Now, we've looked at resistive power, right? Resistive power in chapters 1 and 2. That is the power associated with resistors. Reactive power is the power associated with components that have reactance. Okay, that have reactance, which is basically capacitors and inductors. Now, the reason it is important is because industrial customers have inductive loads. You have big electric machines running constantly, nonstop, sometimes like 24/7 in a factory or a workshop, and these are huge loads. The biggest load in a residential environment is basically an appliance, an electrical appliance. Let's say like a washing machine or a electric dryer, electric or a gas dryer. Those are the two big appliances. And then you have your HVAC unit, okay, the AC and the heating unit. The others, whether it's your, gas range or gas stove or cooking range, your refrigerator, freezer, they have compressors which have inductive loads, but they are not significant enough to actually draw a lot of power. Whereas an industrial customer have tens, even hundreds of machines all running at the same time. All of these machines have electric coils, and an electric coil is an inductor. When you have an inductor, it requires resistive power, real power, as well as power associated with its reactance. The power associated with this reactance is known as reactive power. Okay, it has a physical basis. It has a physical basis in real life, but mathematically we'll model it similar to the way we model reactance, which is using complex math and imaginary numbers. Okay, so again, reactance has reactive power. This power does not actually do any real work. It is set up for the magnetic field, but again, it still has a physical basis in real life. So it requires the inductive load to draw a reactive power from the utility company. Okay. Now, real power, when you're talking about DC, goes from the source to the load. It's a one-way. It's a one-way transmission, right? And over long distances, what happens is a lot of this electrical power transmission is lost as heat. So the overhead electrical lines that we see, they actually dissipate a lot of heat. If you think back to chapter 1, resistance of a material is rho L over A. It is the resistance of a material is directly proportional to the length. It's directly proportional to the length. So while a short wire or a short cable, even going up to like 100 feet cable, would not have any real resistance, if that length is now thousands of miles long, hundreds of thousands of miles long, it has some real resistance. And so anytime electrical power is transmitted over very long distances, it encounters resistance from the transmission lines. When you encounter resistance, it causes electrical power loss. So the point being, if you're transmitting real power, it flows one way, it's consumed, and that's it. But when AC power goes into an inductor, what happens? And we talked about this previously. In an inductor, it flows into the inductor in one half cycle, and the other half cycle, it flows back out. Remember? It flows in and out of the inductor constantly. We'll get to a capacitor shortly after I finish explaining the inductor, okay? But for inductors and capacitors, the power constantly flows in and out. So if this reactive power is transmitted over long distances, what is happening? The utility company sends the power into the inductor in one half cycle, and in the other half cycle, the power flows out all the way back to the utility company, to the source. So the power is being transmitted and is traveling over long distances from the utility to the consumer, which is the industrial consumer. And the industrial consumer, which has inductive load, will transmit it back. So it keeps transmitting back and forth constantly. And every time it travels, it will lose a certain amount of power due to heat. Does that make sense? Right? So industrial customers have to pay for real power as well as reactive power. Residential customers, the reactive power is negligible. Okay, the reactive power for a residential consumer is negligible. Even if you have large appliances, how many times a day do you think you're going to run a washer? Probably once a week, right? If you have a washer or a dryer in your apartment or your residences, at most you might run it like once or twice a week, not more than that. Industrial customers are not only running it every day, but they are running constantly 24/7. So it's a huge amount of power to travel back and forth constantly. Okay, this reactive power does not do any real work. It is used to set up the magnetic field. It is associated with that magnetic field, but it does not do any real work. The real work is actually done by the real power. That is the power that actually gets converted to mechanical energy when it rotates that electrical machine. Okay, so the industrial customers pay for the real power that they consume, but they also have to pay for that reactive power. Plus, the transmission lines, the utility company that sets up the transmission lines, the source, the generators, everything associated with the power generation and transmission has to be able to handle all of that reactive power, which becomes very, very expensive or needlessly expensive, right? So again, it is expensive for both the industrial customer as well as the utility company. Okay, the utility company does not want to send all of this back and forth, neither does the industrial customer, because they have to keep paying for power that is not actually being used. Okay, so the solution is the capacitor. Okay, the solution is the capacitor. So what what they do is, instead of making the power travel back and forth all the time, they install capacitor or a bank of capacitors in front of the inductive loads. Remember, I mentioned last week, power flows out of the inductor, and because a capacitor has opposite phase to the inductor, when the power flows out of the inductor, it will flow into the capacitor. So if you are an industrial customer and you receive the power once, when it sends it out, if you place a capacitor in front of your, it's not technically exactly in front of you, but if you have a capacitor that intercepts that power that's going back to the utility, it now gets stored in that capacitor. Right? You have a bank of capacitors in front. The utility company sends that reactive power once, goes to the inductive load, and then in the negative half cycle, when it goes out of the inductor, it flows into the capacitor. So the next time, in the next half cycle, when the inductor requires power, it does not come from the utility company. It comes from the capacitor itself. And then the power just keeps traveling back and forth between the inductor and the capacitor at the consumer's place itself. It does not go all the way back to the utility company. Does that make sense? And that process of placing a capacitor in front, or the technique of placing a capacitor in front of the inductive load, is known as power factor correction. And we'll expand on that a little bit more in just the next few slides. Any questions so far? Does everybody understand what reactive power is? It's associated with the reactance, does not do any real work, yet it has a physical basis in real life. So an industrial consumer does require reactive power to be sent by the utility company. Okay, the utility company will send it once, but not after that. In real life, if power ever goes out or you're installing a new facility, the utility company will not transmit electrical power all at once. The consumer has to work with the utility company to flip on the switches one by one. Okay, if all of the switches are flipped all at once and all the machines come online all at once, the utility company would not be able to supply all of that power. Okay, so a big campus like Cal Poly or any industrial environment, if a big inductive load goes down, they have to work with the utility company to bring it back online in a staggered manner. Make sense? Right? Now, we are talking about reactance, reactive power, and real power. So I'll tell you that the reactive power plus the real power is represented as a complex quantity. Mathematically, it is represented as a complex quantity. If you read or hear the words that it is reactive power is imaginary, it is talking about the mathematical representation. Okay, it is not imaginary as in, it's not a dream that was summed up by some engineer in the years gone by. It is the mathematical representation. Similar to the way reactance is imaginary, we have reactive power, which is imaginary. Real power is represented by P, which we are already familiar with. Reactive power is represented by Q. Okay, it's represented by Q. And because it's a complex quantity, it also describes this as the rectangular coordinates of a term known as complex power. Total complex power represented by S. All three are uppercase letters. So S equals P plus JQ. Okay, it's a complex quantity. S is the total complex power, P is the real component, and Q is the imaginary component. The units are not the same. Even though they are power, they're all three different quantities, and there is a reason why we keep it separate. Okay. Total complex power is simply volt ampere. Volt ampere. Real power is watts, which we are already familiar with. Reactive power, VAR, is volt ampere reactive. That's it. So again, total complex power is volt ampere. Reactive power is volt ampere reactive, VAR. VAR. Let's take a 10-second pause. Let me know if you have any questions. Any questions? Okay. All right. And since this is a complex quantity, we can draw a triangle with the two quantities, and describe it in what is known as a power triangle. A power triangle. Real power P is on the x-axis. Imaginary power Q, or reactive power Q, is on the imaginary axis. And the line that joins it is given by the magnitude of the total complex power S. And that is mathematically given by the product of the voltage and current, the RMS values of the voltage and current. So VRMS times IRMS. For an inductor, the voltage always leads the current. So the impedance is positive, the reactance is positive. So the reactive power is also positive. For a capacitor, it's the exact opposite. For a capacitor, the voltage lags the current. So the reactance is negative, the impedance of a capacitor is negative, hence the reactive power for a capacitor is negative. Okay. And this opposition between the inductor and the capacitor is why we can actually reduce the consumption of reactive power. The higher the reactive power requirement, the higher the angle, right? And so if you place a capacitor, what happens is, if your inductive power requirement is this much, QL, you can apply a capacitor and bring it down. Capacitor has negative reactive power. It absorbs energy in the negative half cycle and sends it back out in the positive. So capacitor has negative reactive power. And so when you place it in conjunction or in the same circuit as an inductor, it reduces the requirement of reactive power Q. Remember, they're complex quantities. So when you add them, you have to take the phase angles into account. And they're 180 degrees out of phase. If they share the same current, the inductor and capacitor will be 180 degrees out of phase. So if your QL requirement, inductor requires QL, let's say 10, you can place a capacitor in there to supply about 9 units of those. And so the total reactive power required would be only 1. Okay. QL required in real life is never going to be the same every single second. It varies. Okay, depending on the machine, depending on how many machines are running at the same time, depending on the loads, the requirements, depending on the speed, depending on the usage, QL required, the reactive power required by an industrial customer is never the same. And so you place a capacitor which has a fixed value, you try to get it as close to 0 as possible, but they do not want to go above a certain point. Okay. They want to keep that angle. You want to keep this angle as small as possible, but you also do not want to go on the other side. Make sense? Right? Because the capacitor value will be fixed. You're not going to be able to change that capacitor value once it's installed. You can probably bring more capacitors online depending on the design of that circuit, but you cannot actually change the value of the capacitor a lot. So from these triangles, we can have more equations for real power and reactive power. If students have to leave, that is fine. I'm just going to cover a few more slides and then we'll end the class. So based on the trigonometric identities from the triangle, you can describe real power P and reactive power Q in terms of the phase angle theta. Okay. And theta is the power angle. Power angle. It is the difference in phase between the voltage and the current. Okay, the power angle is the phase difference between voltage and current. So it's theta V minus theta I. Okay, that is the power angle. And the cosine of the power angle is labeled known as power factor. This power factor is the important quantity is the most important quantity for a reactive load. Okay. Actually, you know what? Let's end class here today. And then I'll just do this slide and then the example problems on Wednesday. That would be it. All right, I'm still around for questions if students have any. Otherwise, I will see you all on Wednesday.